This section is one of the most important sections that we're going to cover throughout the course of the year. Section 2.7 refers to how you name ionic compounds. Naming ionic compounds is vital, or naming any kind of compound is vital. Throughout the course of this year, you're going to have to name compounds, and you're going to have to write formulas from them. So one of the things we need to learn how to do is go about naming compounds. There are several varieties of compounds, and one of the key factors to identifying how you name them is identifying what kind of compound you're dealing with. Earlier, we talked about the difference between molecular and ionic compounds. We're going to sort of repeat some of those here, and then add a few other types of compounds in that we've not yet discussed. Ionic compounds, we stated earlier, are a combination of a metal and a non-metal. When you name any compound, the first thing you are going to train yourself to do is look at the first element. The first element is crucial to identifying what kind of compound it is. If you look at the first element and it is a metal, you know you are dealing with an ionic compound. Or if you look at the first part and the first part of the compound is ammonium, NH4, then you also know you're dealing with an ionic compound. Now, once you've identified the fact that it's an ionic compound, we simply need to look at a little bit more to that. So let's start off by how we name several types of ionic compounds. The first type of ionic compound we're looking at is an ionic compound in which the metal has one possible charge and a non-metal attached to it. We learned earlier how you can tell the charge of a metal or a non-metal simply by looking at the periodic table. Metals of this type are ones like calcium and sodium, where there's only one possible charge, or transition metals that only have one possible charge, like gold and silver. Sorry, silver, not gold. Metals, when you have a metal with one possible charge and a non-metal, the way we name the compound is as follows. The rule states that we write the name of the metal down, then we take the non-metal with the ending change to IDE. So for example, KBr becomes potassium bromide. K is potassium. We identify the fact that's a metal with one charge. We write potassium down. Bromine, Br, becomes bromide. Let's look at another example of this type. If I have CaCl2, CaCl2, when I look at it, I identify the fact that calcium is a metal. It's on the left side of the periodic table, therefore it is a metal. Cl represents chlorine, so I simply say calcium as the first part of the name. Chlorine, as per the rules, becomes chloride. Alright, so this is how you name a metal with one possible charge and a non-metal. Now, what happens when you have a metal with multiple charges, such as the transition metals? Iron, for example. Iron, when it's combined with a non-metal, or any of the elements that are multiple charge transition metals, when it's combined with a non-metal, the way we name it is very similar to the first way, with one addition. You simply, again, start off by stating the name of the metal. Then, in parentheses next to that, in the middle of the name, you will put a Roman numeral indicating the charge of the metal in this specific case. The second part of the name, then, will still be the name of the non-metal with the ending changed to IDE. So, for example, FeCl2 becomes iron 2 chloride. Now, how do we get that Roman numeral 2 is the big part here. Fe is iron. It has multiple charges. I know that by looking at the periodic table. Once I establish the fact that it does, I put the parentheses in the middle and I leave that blank. Chlorine is chloride. Now, to figure out what went in there and how do I get that 2, I start by looking at the chlorine. I don't look at the metal, I look at what's attached to the metal. Chlorine, from the periodic table, has a -1 charge. But in this formula, there are 2 chlorines which have a total of a -2 charge. We learned earlier on when we were writing formulas that the goal in ionic compounds is for the charges to add to 0. In this case, in order for iron and chlorine to add to 0, iron has to balance the -2 with a +2 charge. Therefore, since there's only one iron to divide that +2 charge by, I say I have an iron 2 chloride. Let's look at another example. In this example, I have AuI3. Au, from looking at the periodic table, is gold. Gold is a metal with multiple charges. Therefore, I simply say gold is the name. And I put my parentheses, which I'm going to leave blank for right now until I figure out the charge on the gold. Iodine is I, so we change that to iodide. To figure out the charge on the gold, I start by looking at the iodine. Iodine from the periodic table has a -1 charge, and there are 3 iodines in this formula. 3 times -1 means the iodine has a -3 charge. Therefore, to balance that, gold must have a +3 charge, giving me gold 3 iodide is the name of the compound. Since these are somewhat tricky and they cause the most problems in most types of compounds, let's look at another example. In our next example, I'm going to start off with Fe2O3. Again, I start by looking at the first element. I identify the fact that Fe is iron, which is a metal, so I know it's an ionic compound. I then look and I realize that iron is a metal with multiple charges because it's in the transition section, and I look above the symbol and there are 2 possible charges there, 3 and 2. 6 is there also, but it is ignorable. So I again start off with the name of the metal, which is iron. And I place the parentheses since there's multiple charges on the metal to fill in later. O becomes oxide. So I have iron something oxide. Now again, to figure out the charge on the iron, I start by looking at the oxide. O from the periodic table has a -2 charge that we learned earlier. Since I have a -2 charge and there are 3 oxygens, that means the total charge on the oxygen is -6. What balances a -6 is a +6. So since iron must have a total of a +6 charge, and there are 2 irons in this formula, that means each one must contribute a +3 charge. The way I get that is 6 divided by the number of irons, which is 2, which gives me a charge of 3. Therefore, my charge is iron, Roman numeral 3, oxide. Please do not write Arabic numerals. That's only Roman numerals in this case. All right, so those are looking at metals and nonmetals, binary compounds. Now, let's look at naming ternary compounds, which are when you have a metal with a polyatomic ion. And very much similar to what we've just done, a lot of the rules are the same, so it's not like learning a whole new set of rules. When you have a metal with a polyatomic ion, again, we follow the same set of rules above. It depends on whether the metal has multiple charges or not. If the metal has not multiple charges like calcium and sulfate, we simply say the name of the metal and the name of the polyatomic ion. Again, this is where it is crucial to know the names of your polyatomic ions. If you know SO4 is sulfate, it saves you time, which you should, again, learn the names, formulas, and charges from the polyatomic ion list. If the metal in the first part has Roman numerals, we follow like the ones above where we have to put the charge in there. So again, if we have CuSO4, Cu is copper, it's a metal, so we write the name of copper down. But since copper has multiple charges, we put the parentheses in the middle, and we look at the second name, which is sulfate. Now the same as above, when we figure out the charge on the copper, we look at the anion, or the negative ion that's attached, which is the sulfate. Sulfate is a -2 charge. I have 1 sulfate. I know I have 1 sulfate here, because there's no parentheses with a number outside of it. Remember earlier when we were writing formulas, we said if you have more than 1 polyatomic ion, you have to put parentheses outside and then put the number of that ion present. But since there are none, that 4 is part of the sulfate. We do not use that 4 to multiply by the -2 to get a -8 charge. The 4 is part of the sulfate. So I have 1 sulfate with a -2 charge, therefore copper has to be a +2, and we say it's copper 2 sulfate. Now, let's look at some examples and go through the rules again to figuring out how we named these. And these examples should be in your notes as well. When naming a compound, again, the first step is to look at the first element in the compound. In all these examples we're looking at right now, they will all begin with the metal, but that won't always be the case. I first look at the name of the element, which is Na, and that is a metal. The next question I should ask myself is, once I establish the fact that it's a metal, is that a metal with multiple charges? If it is, then I know I need parentheses in my name to put a Roman numeral in. If it's not, then I simply do not need that. Sodium is not a metal with multiple charges. It only has 1 possible charge. So to name that, I simply start off by saying sodium is the first part of the name. And chlorine becomes chloride. Our next example, we have Ca and OH in parentheses 2. Again, I start by looking at the first element. The first element is Ca. What kind of element is that? Is it a metal or non-metal? It is a metal. Does it have multiple charges? No, it does not, because it is in group 2A, which is the alkaline earth metals. They only have one possible charge, which is +2. So since it only has one possible charge, I do not need a Roman numeral in my name, and I simply start by saying calcium. OH is a polyatomic ion, so this is a ternary compound. I need to know the name of what OH is. OH is called hydroxide. So the name of this compound becomes calcium hydroxide. Our next example is one that we already have done, so we can go over this one pretty quickly. Fe, I look at the first element. It is a metal. Does it have multiple charges? Yes. So I start by saying the name of the metal, which is iron. I put parentheses in the middle. Chlorine becomes chloride. And again, I figure out the charge on the iron by looking at the chlorine. There's -1 charge. I have 2 chlorines, which makes it a -2. Therefore, iron must balance out with a +2 charge. We say it's iron 2 chloride. Next example, FeO. Fe is a metal. Does it have multiple charges? Hopefully you said yes. So iron is the first part of the name. Since the answer was yes, it had multiple charges, I'm going to put blank parentheses there for right now. Oxygen becomes, again, hopefully you said oxide. If you did not, remember, oxygen, we change the ending to IDE ending. Now, again, to figure out the charge on the iron, we start by looking at the oxygen. Oxygen is a -2 charge. Therefore, iron has to balance that with a +2 charge. Since there's only one iron in the formula, we say it is iron 2 oxide. The last example, CuMnO4. If you want to try to do it yourself before I give the answer, pause on the recording right now, and then you can come back and finish up. Cu is a metal. It has multiple charges. Therefore, the name of it is copper. And I put the parentheses in the middle, and I simply say the second part then, MnO4 is one of my polyatomic ions. Again, hopefully you've studied and know your polyatomic ions and know their charges, because it will make your life far easier when you take the final. And in the chapter tests throughout the course, you will not be allowed to use that polyatomic ion list, and doing so would slow you down tremendously. Therefore, you should not rely on that. You should learn their names, charges, and formulas right now if you've not done so. MnO4 is called permanganate. Permanganate. Now again, to figure out the charge on the copper, I look at the permanganate. Now in this case, I know I have 2 permanganates because there are parentheses outside of it. So that tells me I have 2 of them. Permanganate has a -1 charge. Since I have 2 of them, that's a -2 charge. Therefore, copper must balance out with a +2 charge. Since I only have 1 copper, there's nothing to divide that charge by. So copper is copper 2 permanganate. This is a review again of how you name ionic compounds. So ionic compounds, as a recap, you start by looking at the fact that identifying the first element as a metal. When you identify the first element as a metal, you know you have ionic compounds. If the first element has a metal with multiple charges from the periodic table, then you must use parentheses in the name to indicate what charge is on the metal. Again, it is not telling how many there are, it's simply telling the charge of the metal in that case. The second part of the name comes from what the second part is, or what the anion or negative ion would be attached to the metal. If the anion is a non-metal, one single element like chlorine, bromine, sulfur, then you simply take the name of the element and you change it to an ID ending. So it becomes chloride, bromide, sulfide, etc. If the second part is a polyatomic ion, you do not change anything. You simply state the name of the polyatomic ion. The next kind of compound we're going to look at is actually the easiest to name of all 3 types. In the past, students always find these the most enjoyable to name because they're really easy to do. There's only one set of variations to them. Binary molecular compounds are what we're looking at next. Molecular compounds we learned earlier on was a combination of two or more nonmetals. But binary tells me that I'm dealing specifically with two nonmetals together. When you deal with binary molecular compounds, there's a very basic set of rules you use for naming binary molecular compounds. Again, they're identifiable by looking at the first element. The key to naming any compound is to look at that first element. If you look at the first element and it is a metal, we know that it's an ionic compound from the previous section. If it is a non-metal, other than ammonium, again, you have to train yourself that if NH4 is in the front, that is an ionic compound, that is not a non-metal. If it's a non-metal in the front, we have a molecular compound, and you should use these rules. The rule states the first element will get a prefix indicating the number of atoms in the formula only if there are more than one atom. The second element always gets a prefix based on the number, and the ending will always get changed to IDE, just like it did for the ionic compounds. The prefixes that we speak of are from a Greek list of prefixes, and they are as follows. And again, these prefixes are used for different numbers of atoms, and they are pronounced as follows. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. Now, based on those prefixes, again, the first element will always get a prefix if there's more than one. The second element always gets one, no matter how many there are. So, for example, CO2 is carbon dioxide. The first element is carbon. Again, I identify the fact that there's only one non-metal there. Non-metal, non-metal. Carbon, since I only have one, I don't need the prefix. I never use the prefix mono in the first element. The second element always gets a prefix. Since I have two oxygens, I use the prefix di, and it becomes dioxide. Another example, if I have N2O, again, I identify the fact that it's a molecular compound by simply looking at the fact that N is in the front of the compound. N is a non-metal, which makes it molecular. Since there are more than one in this case, I say dinitrogen. The first element again gets a prefix this time because there are more than one. The second element always gets a prefix. Since the second element has O and there's only one O, I use the prefix for one, which is mono. Now you notice what I do. I don't say monooxide. I am permitted to drop one of the O's. It can be monoxide. So let's look at some further examples. And again, these are in your notes. At any time, if you want to pause and go ahead and try to do them to see if you can get them right on your own and then come back and listen to the rest of the recording, you can do so. The first example, sulfur is the first element. Since there's only one sulfur, I do not need a prefix, and I say sulfur. The second element is oxide, but I have two oxides, so it becomes dioxide. Phosphorus is the beginning of our next compound. I do not need a prefix in this case because phosphorus has only one. The second part of the compound is chloride, but since I have 5 chlorides, I always get a prefix in the second part. So the prefix for 5 is penta. So it becomes pentachloride. Our next example is different. Nitrogen is the first element, but there are more than one in this case. So I do need a prefix in my first element. And I say it is dinitrogen. And the second element always has a prefix. So the prefix I'm going to use is tri, and then I'm going to add oxide to the end of that. Our next one begins with nitrogen. And 2 oxygen becomes dioxide. And our last one, again, the first element does not get a prefix because there's only one, so it's iodine. Now notice in the first element, I'm not changing the ending. I did not change that to iodide. That is a common mistake I see. The first element is just simply the name of the element, iodine. And pentachloride. fluoride is the second part. As a recap then of molecular compounds are two nonmetals. These are dealing with binary molecular. Again, the prefix binary means two. Nonmetal, nonmetal. First element will get a prefix only if there are more than one in the compound. The second element will always get a prefix and the ending change to IDE. The prefixes are your responsibility. You are expected to know those prefixes based on those numbers. Again, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. The third type of compound we're going to look at naming are acids. Acids are a compound we haven't looked at so far, but they're one that you've heard about frequently in society. Acids are the easiest to identify, but maybe they become the most confusing to name. Really not too bad once you get the hang of it, but there's just a wide variety of acids that exist. Now, the good thing about acids are there aren't a whole lot of acids that we use for the most part. Acids are two types. We come in what are called binary acids and oxoacids. A binary acid is when you have hydrogen plus another nonmetal. So if you have hydrogen and another nonmetal, you have a binary acid. Now, in general speaking, these will come in two forms. They will come in what is called a gaseous form, and you'll have a G symbol shown with them, such as this example right here. Or they'll have an AQ written in them, which means aqueous. Aqueous from the Latin word meaning water, means they're on a water base. They're a liquid form. It becomes real easy in these problems because very rarely are we dealing with gaseous acids. For the most part, over my career of 20-some years in chemistry, I have hardly ever encountered or used gaseous acids. Only in certain problems have I had to deal with them out of a textbook. So for the most part, when you're dealing with acids, this is the one you're most frequently going to see, are the aqueous states. Nonetheless, we are going to learn how to name both of them. When you have hydrogen in front, they are easy to identify. So we've said all along that when you name a compound, the first step is to look at the first element. Hydrogen in the front simply indicates to you automatically, there's no question about it, that you have an acid. The next thing you need to determine is what kind of acid do you have. Do you have a binary or an oxoacid? If you have a binary acid, you'll have hydrogen with simply one other element. Hydrogen with chlorine, hydrogen with fluorine, hydrogen with bromine, something along those lines. You then need to look at a state symbol. If you have a gaseous state symbol, a little G shown, you simply name it the way you did an ionic compound. You start off by simply stating the name hydrogen, plus adding the word chloride in this case. So HCl becomes hydrogen chloride. HF would be hydrogen fluoride. HBr would be hydrogen bromide, so forth and so on. If there's an AQ symbol with it, we name it slightly different to indicate the fact that it is an acid in aqueous format. We start with the prefix hydro. We take the root of the nonmetal, we add IC to it, and then we add acid to the end of that. So HCl aqueous becomes hydro, chlor from chlorine, ic, acid, so hydrochloric acid. HF would be hydrofluoric acid. HBr, hydrobromic acid, so forth and so on. All right, so again, most of the time you're dealing with AQ. If you are not given a state symbol, this is very important. If you are not shown a state symbol or not told a state symbol in a problem or in a expression, you should always assume that you have an aqueous format. All right, so if no state symbol is given, always assume that you have an aqueous format. Now, the second type of acid we're going to deal with then are called oxoacids or oxyacids. You'll hear them referred to. An oxyacid, again, begins with hydrogen. That's what identifies the fact that it's an acid. The ending part is what is different. Instead of having a nonmetal, you have a polyatomic ion, one of the polyatomic ions that exist. Now, again, depending on what your polyatomic ion is, will depend on how you name your acid. If the polyatomic ion ends in ATE or IDE, we'll name it one way. If the polyatomic ion ends in ITE, we'll name it another way. If it ends in ATE, we change it to ic and add the word acid. So for example, H2SO4, sulfate is the ending. So we take the root of sulfate, which is sulfur, and we add ic to it. So it becomes sulfuric acid. Now notice in this name we don't mention the hydrogen anywhere. So sulfate becomes sulfuric acid. A little expression I always like to give my students to remember that is a little expression that says, I ate it and it was icky. Ate it and it was icky. It means ate changes to ick. Or I'd eat it, but it's icky. All right, so I'd or ate changed to IC in the ending. If the polyatomic ion ends in ite, then we would change it to OUS ending. Same rules apply. Root of the nonmetal, polyatomic ion, and then OUS added to the end, and then the word acid. So for example, if we have H2SO3, SO3 is sulfite. So sulfite, the root of that polyatomic ion is sulfur, it becomes sulfurous acid. All right, so ite goes to OUS. Now let's look at several examples to go through. And again, as we've done before, you are welcome to pause if you want to the recording right now and then go through and see if you can answer them on your own, and then come back and see how many you got correct. The first example, HCl. Again, HCl we talked about briefly above, but in this case there's no state symbol shown. When there are no state symbols shown, we again say that we should, that's correct, assume aqueous. So this would be hydro as the root, chloric acid. Next example, we look at the front, we see hydrogen. Again, that identifies the fact that it's an acid. So we know we're not dealing with ionic, we know we're not dealing with a molecular compound. It is an acid all the way. Is it a binary acid or an oxy acid? It is oxy in this case because it is a polyatomic ion with a hydrogen. So we look at the name of the polyatomic ion. ClO4 is called perchlorate. Perchlorate, we take the root of that and we change it to perchloric acid. Remember, I ate it and it was icky. So we change that to perchloric acid. Our next example, H2S, again, acid begins with hydrogen. Binary acid because the second part, the anion, the negative ion, is a non-metal, not a polyatomic ion. So therefore we simply say hydro. Oh, excuse me, that's getting sloppy. Hydro. We take the root of that, which is sulf. Acid. So it becomes hydrosulfic acid. HCN, acid, polyatomic ion on the end. CN is a polyatomic ion, therefore we use the polyatomic ion rules. In this case, CN is cyanide, so we follow the 8-ide rule. So it becomes cyanic. We drop the IDE and change it to IC and add the word acid. So it becomes cyanic acid. HNO3, polyatomic ion. NO3 is called nitrate, therefore it becomes nitric acid. HNO2, nitrite is the polyatomic ion, therefore we call it nitrous acid. Again, as a summary of acids, acids always begin with hydrogen. That's your identifier. When you see hydrogen in the front of a compound, you know you have an acid. That is the key identifying factor. There are two types of acids, binary acids and oxyacids or oxoacids. Binary acids when you have hydrogen and a non-metal, and they will come in two forms, gaseous or aqueous. Again, most of the time we deal with aqueous, and you should know the different rules for those. If they are a polyatomic ion attached to the hydrogen, then you look at the endings of the polyatomic ion. If the polyatomic ion ends in ate, you simply state the name of the polyatomic ion with the ate changed to ick, and then add the word acid. If it ends in ite, you change the polyatomic ion name to us, and you change it to add the word acid as well. We just finished talking about how you go from formula to name. We looked at all the different ways to do that. It can be quite complex and a little bit confusing because of all the different ways you have to go from a formula to a name, and you have to know the variations of the different naming techniques. You have to be able to identify if it's an acid or an ionic compound or molecular compound. And then once you identify those, you have to identify what type of acid it is. If it's an acid, you have to identify what the polyatomic ion ends with. There's a lot of different variations. Going from name back to formula is a little bit easier. It's a little less complex. And Fortunately, it's what you spend most of your time doing, is looking at a name and writing a formula from it. When you're going from a name to a formula, there are really only two ways you look at them. One, I say, is easy, one is easier. All right, so let's start by looking at the easiest of the ways going from name to formula. The first thing you look at in a name to determine how you're going to write the formula out of it is, do you see prefixes or not? And by prefixes, I mean the prefixes we use for molecular compounds, the mono, the di, the tri, tetra, all those. If you see prefixes in the name, it's very easy. You simply write the compound as the prefixes would tell you to do. For example, carbon dioxide. Well, in the name, you see the two elements that you're going to write. So we're going to write a carbon, we're going to write an oxygen. We know those two things are in the compound. By looking at the prefixes, we know that the first element has only one carbon, so we simply say C. And then dioxide requires us to know the prefix di means two. What does that mean? It means we have two oxygens. So carbon dioxide. Let's look at another example. Dinitrogen trioxide. Again, first thing I notice in the name is prefixes. When I notice the prefixes, it's very simple. I simply write it as I see it. Dinitrogen means two nitrogens, so N2. Trioxide, tri means three. Three what? Three oxygens. So we write O3. And let's try one last example. Oxygen hexafluoride. Again, in the name I see hexa. Hexa tells me that this is a binary molecular compound, and I don't need to worry about anything except for writing it as I see it. So oxygen is the first part. There are no prefixes, so therefore I have only one. Hexa means six. Six what? Fluorines. So OF6. All right, so that's the easiest of the ways. If you're giving a name going back to a formula, if you see prefixes, you simply do that. All other compounds require the second set of steps. In all other compounds where we don't see prefixes, we simply are going to revert back to what we did earlier, where we're writing ionic formulas, because we're dealing with ionic compounds. So the first step you're going to do is you're going to write the two symbols for the particles that make up the compound. Then you're going to determine their charges, just like we would have done earlier. If it's a metal, you'll simply look at your periodic table and figure it out. If it's a non-metal, you'll look at your periodic table and figure it out. If it's a polyatomic ion, again, I can't stress enough, you should know the charges of the polyatomic ions and be able to write them. So in our first example, we have calcium chloride. CaCl are the two symbols. So I write down Ca for calcium, Cl for chloride. Now, it's not done there. I don't just put them together and say CaCl is my formula, because we have to balance the charge. Ionic compounds require the charges to be balanced and add to zero. So from the periodic table, I put +2 for calcium, -1 for chlorine. When we revert back to what we've done earlier, we do a crossover method. This 2 is going to come down here, this 1 is going to come down here, and then we put the two things together. Remember our exceptions to the crossover method as well. If you have like charges, then you cancel them out. You simply put the two elements together, for example, +2, -2. Or if the charges can be reduced, you reduce them first and then put them together. So calcium chloride's formula is CaCl2. In our second example, we have iron 2 nitrate. Again, I write down my symbols. Fe is iron, nitrate is NO3. So once I have them written down, I know I have to next figure out the charges. Now, remember from earlier that this 2 does not mean that I have 2 irons. It simply means that the charge on the iron in this case is +2. That's important to us because we can't look at a periodic table. If you looked at the periodic table, you would be inclined to use the +3 charge for iron because that is the most common charge. However, in this case, we've been told that it's exactly 2, so it's iron +2. So we have Fe +2. Nitrate is one of our polyatomic ions, and it has a charge of -1. So knowing the two charges now, we can do the crossover method, and we end up with Fe, bringing the 1 down, but we don't have to write the 1, NO3 in parentheses 2. Again, anytime you're putting a number with a polyatomic ion, you have to put the polyatomic ion in parentheses first. One last example. In our last example, we have cesium phosphate. Cesium is Cs. Phosphate is PO4. So that's the first step, writing down the particles that make up the compound. The next step is to write their charges, +1 and -3. Again, if you don't know those off the top of your head like I do, you can simply look up the element on the periodic table of cesium. And again, phosphate, you should take time to learn those charges. Once I know I have +1 and -3, again, I do the crossover method. The 3 is going to come down to cesium to form CS3. and the 1's going to come down with phosphate. Since it's a 1, I don't need to do anything, and I say PO4. So that is the formula. So again, in summarization of writing formulas from names, it's a little bit easier. It's less complex. You either use the easy way or the easier way. The easiest way, or the first thing you do in writing a formula to a name to a formula, is you look to see if there are any prefixes. If there are prefixes, you simply write it as you see it, using the prefixes as your guide. If there are no prefixes in the name, the mono, di, tri, then you will write the 2 symbols down that make up that element. You then will figure out their charges from the periodic table or from memorization of the polyatomic ions. And then you'll do the crossover method again and rewrite the formulas.